In the following class, this lecture is used. You have seen it, right? Exactly. So I want to pick up just another point so that it will be helpful because we will be using this. This is Maxwell's distribution, is chapter 2. Maxwell distribution, you all of know it, I think, and you have used it in so many texts. I just want to remind that we will be using the Maxwell distribution. Actually, the neutron. Okay, yeah, we are here. The neutron distribution, neutron acts like gases and it follows the Maxwell distributions. The Maxwell's distributions, all of you know it from first year, I think, that Maxwell distributions. In gas, the energies and atoms, molecules are distributed according to Maxwell distribution. This is the famous distribution. And if the function is n of E, is the density of the particles per unit energy, then NED is the number of particles. Of course, this is the volume, and is the number of particles per centimeter square, and then you multiply it by DE, the particles per unit volume, having energies E plus D. That is the energy spectrum. You divide it into some, what I should say, discrete intervals, like, we will talk more about the discrete energy system. So this is, you just discretize the energy spectrum. So this is energy E plus DE. You understand this? And this NE, according to the Maxwell distribution, which we all know, that NE is this twice pi n, pi kt to the power 3 to e to the power half e to the power minus e by kt. You have, I think, used it so many times. So I'm just touching it because we'll be using this in our reactor physics. Here in this equation, and is the number of the particles per unit volume, which I already said, and is the particle density, that is the particle density. K is the Boltzmann constant, we all know it, which has the unit of energy per degree Kelvin. This is always in Kelvin, so this is the energy, which is the unit is joule, or if you put it in EV, it will be 10 to the minus 5 EV per degree of Kelvin, 8.06. So this is the value of K. We know this value of how to calculate. And as in the, we'll be using in EV, so it is better to put it in EV. And T is the absolute temperature of the gas. All of you know it, the function. And if you plot the function, you will get a plot like this. You know the Gaussian distribution. Okay, this is your Gaussian distribution. Actually, why here we are using the Gaussian distribution? Actually, when we'll see the spectrum of the neutrons that come out in our fission reaction, we'll find a similar distribution. Okay, so there we shall have to use it while solving the transport equation and or the diffusion equation for various energy regions, say fast and thermal and so on. We will use it. That's why I'm just using it. So in that case, the energy distribution functions are more complicated. Well, for solids, however, it can be used for solid. The difference is small. The temperature about 300 degree Kelvin, above 300 degree Kelvin, the difference is very small. At the temperature, if it can be assumed, they applies to solids and liquids and gases. So we can say that above 300 degrees, that is how much, about say 20 degrees or so, it applies this Gaussian distribution. You can apply with some approximations to solid, liquid, and gases. And however, we will be using it for neutrons, and neutrons will be treating it like a gas. So we can apply this. And the most probable energy, this is the most probable energy, right, at the height. So this is the most probable energy. The most probable energy in the distribution is such 1 in 2/5, that is as defined, we have already maximum of the curve. This is the maximum of the curve. This can be calculated by placing the derivative NE equal to 0. If you put this derivative equal to derivative of equation number 2, if you put equal to 0, you get this can calculated by placing the derivative of NE to equal to 0, the most probable energy EP. Now we want to calculate the most probable energy EP in the Maxwell energy distribution is then easily found to be, if you put this equation number 2 equal to 0, you will get EP, that is the most probable energy equal to half kT. Okay, so this is very important information for us, that EP in the Maxwell distribution, the probability of the maximum energy is half kT. However, the average energy, and we are interested also to know the average energy, E is defined by the integral, that is E average, definitely it will, this integral divided by 1 by L, as we are averaging it. And this will be, this is Maxwell distribution. We'll always keep this in mind. We shown the fixed fission spectrum that we'll be talking very soon. The fission spectrum, well, almost like this. Okay, so we can use this Maxwell distribution. Now, this average, carrying out the integration of this, and we get the average of the energy of the gases is E per equal to 2 by 3 kT. That is 2 average energy equal to 3 kT, right? This combination with the kT, someone please mute yourself. Often appears in the equation of nuclear engineering or physics. Engineering and physics is the same for. I said physics is the part of the core of engineering. Calculation involving these parameter are then expedited by, remember, T0. Oh, I know what is T0. You all of know it. 293. Okay, and has the value of KT0 equal to 0.03 EB, which is about 1/40th of KT0. T equal to 0, that is 293. If you put 293, 275 is K, that is around 20 degrees centigrade. This will be around 20 degrees centigrade. 20 degrees centigrade. This is energy is 0.02 eV. Actually, in thermal neutrons, this is the, actually we define the neutrons. If it has this 0.0253 eV, we call it a thermal neutron. There are fast neutrons, thermal neutrons, intermediate neutrons, and also of course there is a big spectrum. Then you discretize it. There can be, in cross sections calculations we use thousands of groups and then condense it to multi-group, from the multi-group to the few groups, and then the constants, that is the cell constants, and then we do diffusion equation. Or if we calculate the transport equation, we use this, say about 200, 300, 500, 5,000. In MCNP, they use 5,000, around something like 5,000 groups of energy of the spectrum. The spectrum starts from 0, that is from the thermal 0.02. This is the energy 0.0253 eV up to 20 MeV. So you get, these are very simple equations. So you shall have to keep in mind the average energy is 2/3 kT, and this is thermal at 293, that is 20 degrees centigrade for you. Which if you put it to neutrons of energy, it will be about something like 22,200 meters per second. You just can calculate, you just to understand this, you as an example, what are the most probable and average energies of the air molecules in New York City subway in summertime. Say the temperature is 38 degrees centigrade. A few days we had 38 degrees centigrade. So what was the energies of the molecules in the air in the Dhaka city. So you can just calculate. K is K will be in degree Fahrenheit, 3 plus 273, you know. So it follows that the temperature of air is 311, blah, blah, blah. And then EP, you just use this equation, EP, you have got this equation. EP is half KT. And this is the maximum energy, and from this you can calculate, from this EB, you can calculate, finally get the E average equal to 3 EP, so we get is 0.02 EP. So energy of the molecules at 38 degrees centigrade is average energy of 0.0402, little bit above than thermal energy, 0.04. The thermal is 0.02. Well, so that's it. We will be using it. That's why I'm just reminding you, and I'm sure that all of you know it. Don't think that I underestimate your knowledge. Definitely you know it, but just since we'll be using it, we just remember these two equations, the Maxwell equation and the average energy and the maximum energy. Okay. Next, we move on to chapter 3. So that's the over with chapter 2. There are lots of other things, but you know, I try to follow the sequence. This we have done already. You have done this problem particularly. This one is very important. And I will give you a problem solved. This one, you remember that we did in steps, but you can do in other ways also if you can, but try to get the same answer. And after that, we move on to chapter 3. Interaction of the radiation with matter. Actually, we will not talk much about other radiations like, say, the betas and gammas. We'll be mostly concentrating on neutrons. And others, you have studied, I'm sure that you have studied the interaction of the gamma radiation. There are 3 important radiations in gamma radiations. What are those? You remember, recall? What are the 3 most important interaction of the gamma radiation with matter? You recall someone? If you would recall, Compton, pair production, and what else? Compton scattering, pair production, and another one.
Pair annihilation.
I beg your pardon? Okay, go ahead.
So pair annihilation?
Annihilation, that is pair production. Annihilation is pair production. Right, exactly. This is important. I did not tell you because, you know, Einstein got Nobel Prize on photoelectric effect, right? So these are the important. And there are lots of other gamma radiation interactions, around 12 or I think 20 interactions. But we will be concentrating mostly on neutrons because the design of the nuclear systems, that is the nuclear reactor, radiation shields, are very important, you know. You shall have to protect yourself. And generators, neutron generators, we use for produce isotopes, and accelerators, all accelerators depend on the interaction of the radiation with matter. For reactor, neutrons of 0 to 20 MeV, remember 0 to 20. Actually, 0 to 10 is also okay, but the tail goes up to 20 MeV. So our interest for the neutron is from 0 to 20. Well, we don't go for higher energy neutrons, it has other applications. But for reactor technology, we will be concentrating on 0 to 20 MeV. For neutrons and some charged particles, we will see some charged particles is our concern. And most radiation in nuclear systems fall in within this range, 0 to 20. So we are, and so I just told you we have some charged particles also. And there is a basic difference between the charged particle interaction, I told you, and the uncharged particle. Neutron is an uncharged particle. And we will have alpha, betas, and other charged particles, protons, and neutrons, and etc., etc. So these have definite range. This is the basic difference between the charged particle and interaction, charged particle interaction and uncharged particle interaction. For uncharged particle, it's an exponential function. And for charged particle, it has a definite range and definite energy. And if you put the same thickness, then 100% of the charged particle will be stopped. 100%. So we be on the conservative side, we put in shielding practice particularly. We put little bit, say 0.001 millimeter more. Then you are sure that 100% of the particles are stopped by your shielding. But if it's less than, say, by this amount, 0.001 millimeter, then 100% of the particles will pass. So for designing your shield, you shall have to exactly know the range of the uncharged particles, and the shielding will be exactly the same, little bit more to be on the conservative side. And if it is less, you shall have to be careful. You remember that 100% of the particles will pass. That's why it has a definite range and for a definite energy. I think you already know this if you have studied in undergraduate courses. Actually, the course that we are, when you will go outside, inshallah, for your higher studies, you will see that these things are actually undergraduate stuff. Actually, the routine, the syllabus that we have, it's meant for the undergraduate students. We did it in our master's class, but you remember that 30, 40 years ago, our master's was undergraduate, like just graduate, or undergraduate, 4 years. So undergraduate is 4 years. So that's why that syllabus, I studied the same syllabus. It didn't change much. I talked to the department, but anyway, you cannot change the syllabus. And also, because if you want to go for higher reactor physics, these things that we are doing is the basic foundations, elementary elements that will be necessary for reactor physics, as you have seen. So if you, in real sense, if there was a real reactor physics course, then this would have been in undergraduate course, and then we could move to a advanced course. We at the end we can touch a few of the topics of the graduate courses, but let's see how far we can go. Our today's lecture is lecture number 9. Actually, we have 3 lectures, so we shall have to divide. We are taking two classes each day, so accordingly, you just have to normalize this to 3. So many lectures we have done. So now let's talk about the neutron interaction. First thing, the neutrons are uncharged particles. So it can pass through the electron cloud. A nucleus, in the nucleus, around the nucleus, there is an electron cloud. So since this is electron, is a charged particle, and this neutron is uncharged particle, so it can definitely penetrate the electron cloud and interact with the nucleus, with the nuclei of the nucleus, not atom. So the neutron interacts with the nucleus or the nuclei, that is the proton, that is the variance, that is the protons and neutrons of the nucleus. This interaction is appears with the same energy, and the nucleus also is in ground state. So actually nothing happens as far as the neutron energy is concerned. The neutron in this case is said to have been elastically scattered. So we just say in this case, if the neutron strikes the nucleus and the neutron reappears, the neutron strikes and neutron reappears, and there is a conservation of energy, and there is a recoil nucleus. We will talk lots on this elastic scattering. Okay, later. Okay, because this is a very important subject for the reactor, because we shall have to talk. We have the fast neutrons in all of the neutrons that are appearing in the nuclear fission is fast neutrons. So we are talking about thermal neutron, thermal reactor. So we need thermal neutrons. So we shall have to moderate it. So we will talk about the moderating power, moderating ratio, and so many other stuffs. So this is elastic scattering. That is, this neutron is reappearing. Definitely, it is sharing its energy. It's a billiard ball like. It's a billiard ball like reaction. Yes, it scatters. It is elastic scattering is possible when this billiard ball you have seen that the size of the ball is same, so that they can share energy. So the neutron that is coming out after the scattering, after this elastic scattering, might have some less energy. And actually, this is the technique, and this is the reason that elastic scattering is very important, because we see that this elastic scattering, we lose energy. Actually, the neutron diffuses, scatters with the low number of nuclei, like say hydrogenous material. That's why hydrogen is a good moderator, because the hydrogen nucleus is small, right? Say carbon, it is also a good moderator. We will see the moderating ratio and moderating power. Then we can easily identify that which one is the good moderator and good E. And also we'll talk lots on this, as I said, the energy sharing of the neutrons. But just we know for the time being that there is an elastic scattering, and in the elastic scattering, the neutron strikes the nucleus, which is almost in the ground state, and it reappears with the same energy. It appears, the neutron reappears. Maybe the energy is not different, but the energy is conserved. Energy conservation, kinetic energy is conserved. Momentum and kinetic energy is conserved. So what we say there, and this is a very extremely important, I should write this sentence, that this is a very extremely important, because this elastic scattering. So first we get elastic scattering. Elastic scattering. I have defined elastic scattering, and in the book they have given it. But this is extremely important, because only interaction process along with radiative capture. Along with the radiative capture, we'll talk about radiative capture just in a while. With radiative capture that can occur at any neutron energy. So this is extremely important. I said that this elastic scattering, we use it for moderating the neutrons, that is to bring the neutrons in the thermal region. And that's why it is very important, and it is very মজার ব্যাপারটা হচ্ছে যে it can interact almost this interaction, this elastic scattering and radiative capture can interact with the nuclei at any energy of the neutrons. That's why it is very important. So this is a very important point to note, extremely important. Extremely important, because only as this is the only interaction along with radiative capture. We'll talk about radiative capture. Radiative capture can occur at any energy of the neutrons. Okay, so I hope that you can read it. So this is an important point. So it plays a vital role for moderating, and it at a point. Another point is it plays a vital role. Plays a moderating neutrons. To thermal energy. So this is very important. What else for this interaction? Okay, so actually this interaction, momentum and kinetic energy, momentum and kinetic energy of the system, of the process is conserved. Okay. So, well, this is the two important thing that we know. Okay, we just keep in mind, since we will be using this property. As I said that we will talk a lot on this, and these two types are resonance scattering . Resonance scattering, and another is potential scattering. Resonance scattering and the potential scattering. I hope that you can see the board. Do you see the board? Someone, would you please volunteer? You can.
নিচের লাইনগুলো দেখা যাচ্ছে না, একটু নিচে নামাইলে ভালো হতো।
এবার দেখতে পাচ্ছ?
জি স্যার।
It plays a vital role in moderating the neutrons. And the second is momentum and kinetic energy conserved. Okay, that's why it is. And actually, we shall have to write all the interaction in conventional form. That's why we call it this. So there are two types, okay? Just follow this. There are two types, resonance scattering and potential scattering. We'll talk about the resonance and potential scattering later. Potential scattering, resonance scattering is that we know the energy states. When the energy of the incoming particle is equal to sum of the energies of the energy state of the nucleus, that then there will be a resonance scattering. And this is resonance scattering, and the potential scattering is that we know that this is the nucleus. This is the nucleus. Nucleus has what? The potential wall. You remember that the nucleus has potential wall. So there is a potential around there is this potential field of the nucleus. So what happens? This nuclear, that is, if this is the nucleus, this is the nucleus, and this is its potential, like this. This is its potential wall. This potential wall. Then the neutrons come. Neutron comes, and it does not go inside. It goes back from here. This is incoming neutrons. It works with the potentials of the nucleus, and that's called potential scattering. We will talk about it later when we study the cross section. Okay, so this is potential scattering, and potential scattering is very important because most of the interaction in thermal energies, for long range in the thermal energy, it is potential scattering. As I said, that I will show the picture when we talk about this. And since this work with the outer surface of the nucleus, so with this you can actually find out the radius of the nucleus. This is very important. Okay, we'll talk about it. So this is elastic scattering. For the time being, this is enough. Because we shall have to talk a lot on this. Okay, and then comes the inelastic scattering. There's the same process as the elastic scattering, except that the kinetic energy is not conserved. So the momentum and the kinetic energy is not conserved. This is inelastic scattering. If I go back to the book, let's share. Where is share? My sharing, share screen. This is elastic scattering, and in elastics then, elastic scattering, we will always write in conventional term, and we call it N reaction. N reaction. What does this mean? That a neutron is coming and another neutron is the incoming. In the bracket, this is incoming and this is outgoing particle. This is incoming particle, this is outgoing particle. So this is N symbol. The symbol is N. So in the elastic scattering, we call N scattering. Okay, the symbol is N. So the inelastic scattering, it is. I'm just going through the book. The process in inelastic is the scattering, except that it is the same process, the elastic scattering. The nucleus is left in excited state. So what it happens that it is coming and the nucleus is neutron. That is, it shares some energy with the nucleus. Because the energy is retained by the nucleus, this is clear in endothermic reaction. You understand what is exothermic and endothermic interaction, and elastic scattering is denoted by N prime. The inelastic scattering, so this is the inelastic scattering is N prime. We call N, this is elastic scattering, and inelastic scattering N prime, because this N prime will be this N prime will have, and since it shares this energy, so this will be different, and that's why we call it the inelastic. So when we will see N prime, we will understand that is an inelastic scattering. Okay, there are lots of other we shall have to talk a little bit more about the inelastic scattering. The excited nucleus decays. So what the nucleus is, so the nucleus is in excited state. So what will happen, this excited state, the nucleus must come to the down, it will have a natural tendency to come to the ground state. In that case, it will come to ground state with the emission of a gamma rays or in inelastic, and these are called inelastic. They are called inelastic gamma rays. So if in inelastic, we can have N prime, and also we can have, in addition, we can have gamma radiation after the interaction. So this is inelastic scattering. Okay. So at high energy, actually the inelastic scattering, the mechanism is that this inelastic scattering happens fast when, most of our neutrons that are produced in the fission reactions are fast neutrons. So the fast neutrons, what happens with the heavy elements or even intermediate range elements, it first makes an inelastic scattering, and energy, a lot of energy is shared. Then it comes down to the lower energy range, and then elastic scattering occurs. So this is the mechanism. The first, it makes an inelastic scattering with, but it should have high energy. It has a threshold energy that it should have some high energy. At high energies in MEB, inelastic scattering occurs. So the inelastic scattering will say N prime. This is when we see this N prime, we will say that this is an inelastic process. And at high energy in MEB, it occurs, this N and this occurs at high energy. At high energies. And kinetic energy is not conserved. This is another important, the kinetic energy is not conserved in this case, whereas in the case of elastic scattering, the kinetic energy is conserved. So this is I think for the time being, this is enough to know just what is the difference between the elastic and elastic scattering. It honors elastic scattering usually occurs at the low energy, the low Z element, and the elastic scattering occurs at high energy, usually with the high, let's say, iron. If a neutron comes, even the thermal neutrons comes, or say some neutron will come and comes with say intermediate energy. Then if it hits iron, then what will happen? It will emit a gamma radiation, and that gamma radiation will be 7 MeV. So then the headache will be more on gamma radiation that this neutron is producing. So that's why we shall have to know this mechanism more accurately and more in detail. So we will discuss about in more detail. So we're just talking about the process. So this is another is an inelastic. inelastic scattering. So we have elastic scattering, inelastic scattering, and another is the radiative capture. In elastic scattering, it may so happen that the neutron will come and then make a compound nucleus, and then it will decay to, it will come out with another energy at N prime. So there is another possibility that it can form a compound nucleus. Then we have, I think this is enough for the inelastic scattering for the time being, because we shall have to go in depth about it. And then we have a radiative capture. This was number 2. Number 3 is radiative capture. Radiative capture means that the neutron comes and the gamma radiation, neutron is absorbed. So if we divide the absorbed neutron in 2 types in generally, in which the neutron is absorbed and in which neutron is not absorbed. So in this case, the neutron gets absorbed and the gamma radiation goes out. So what we can say that this is an N gamma reaction. The neutron is the incoming particle and the outgoing is the gamma particle. Okay. The neutron is captured by the nucleus. The neutron is captured by the nucleus, and one or more gamma radiations. It can be 1 gamma radiations or more than. That is the energy of the gamma radiations can be different for the different states of the energy potentials. The energy states for different energy states, we will get the different gamma radiation. I'll show you the picture. There are lots of pictures in this book also. So our gamma rays are emitted and called these capture gamma rays. So these are called capture gamma rays, radiative capture. And some original neutron, the original neutron that came, it is absorbed, and this process is an example of class of reactions that known as absorption reaction. So this radiative capture actually is an absorption reaction. There are only 2 types of absorption, and in one it is neutron is absorbed, because say we will see that there are another type of reactions can be also absorption, can absorb. Okay. So I hope that now you understand what is the radiative capture. The neutron comes and it gets absorbed in the nucleus, and we get a gamma radiation or several gamma radiations, depending on the energy state of the nucleus that it hits. Okay. And such reactions, these N gamma reactions can be both exothermic and endothermic, depending on cases. So it can be both exothermic and endothermic. These reactions, actually, if I could give you the IAEA lecture series, these are all documented very nicely, very precisely, and it is simulated. You can see this elastic scattering, radiative capture, they have animated. So there is animation. So hopefully we will get it. I don't know how to get it done, how to convey it to this material. We shall have to do it. We will try, well, inshallah. I hope that someday, very soon, we will be able to talk, and even if you can come to the department, we can share it. So this is number 3, okay, is radiative capture. Number 4 is charged particle reactions. It can so happen the neutron is come, charged by the neutrons may also disappear as a result of the absorption of the particle, and some charged particles like alpha and proton can go out. That is, the outgoing particle can be alpha particle or a proton, etc., or any charged particle, any other charged ions. Okay, and that's why we call it charged particle reactions. you are seeing the book, so I think I shouldn't write this thing. So this is the charged particle reactions. So the charged particle can be reactions can be an alpha, it can be NP, that is the neutron coming and the proton going out, or it can be an neutrons, neutron coming, neutrons going out, etc., etc. Okay, such reactions may exothermic. This can be both, as I said, that this can be exothermic and endothermic. Remember that the reactions, if they are exothermic or endothermic. Okay, so this is charged particle reactions. I'm trying to finish this, and then we have neutron producing reactions. Okay, this is very important. Reactions of the type N2N, neutron producing reactions. So I just write N2N. Number 5 is N2N or N3N or more. Okay, N2N or more, N3 and so on, blah blah blah. So in this case, what happens is that this happens with the energetic neutrons, the neutrons that have, because it is extracting some neutrons from the nucleus, so it must have a threshold and it must be endothermic, since it needs energy to reaction to one neutron to, it can be N2N or N3N, etc. It says that reactors are extracted from the nucleus. And N2N reaction is especially important in reactors containing heavy water or beryllium, since hydrogen and beryllium, you have seen the, you know the beryllium reaction. With the beryllium, we know, we have studied just before in the previous lecture, we studied the N beryllium reactions have loosely bound neutrons. This hydrogen that is with another extra proton, that is the neutron and the beryllium, are very loosely bound. That's why this reaction, the N2N reaction, exceptionally important in reactors containing heavy water. There are heavy water reactors, na? You know, LWR reactors, light water reactors, or heavy water reactors. Light water reactors are PWRs and BWRs, and heavy water reactor is PHWR, or we call it heavy water reactor, PHWR. So there are lots of PHWR reactors, heavy water reactors around the world are working. So these in the N2N reaction, these reactions are very important. But these two reactions, this hydrogen and beryllium, let's see, you remember that what happens, and these photoneutrons that we talked about, that is the charged particle reaction and the neutron producing reactions above, so it even has a threshold. Above this threshold, the cross section increases with the energy. Above this threshold energy, it increases with the energy, and it reaches the top around 20 MeV. Then it decreases. This is the threshold cross section with the energy E. And this reaction is well, it's in the book early. I want to add something here, because these reactions, if it happens so that if it comes out with some neutrons, some neutrons, we call it neutron producing reactions. I talked a little about the neutron producing reactor, and I gave you a work that, or you can study this neutron producing, what are the neutron produced reaction, and we studied this beryllium. We did not write this reaction, but this can be a reaction. Like say beryllium beryllium 4 or beryllium 4. It is with beryllium 8. Not beryllium 9, beryllium 8. No, this is beryllium 9. So this can be a beryllium 8. Beryllium 8 4. There will be no change in beryllium 8. And plus, what else? We have one. We see that there is one extra neutron, so this neutron is coming out. So this is beryllium 8, or this can be actually this can be beryllium 8, or it can be two. It can be two helium. It can be two helium nucleus. Two helium. Helium is 4. Is 2 into 4 into 2. So it can be either beryllium 8, or even it can be helium 4, two nucleus of helium 4 and neutron. So we see that this neutron is coming out, the photoneutrons. So, and in this case, okay, why I said this beryllium and hydrogen are important. And let me write the hydrogen reaction, the deuterium reaction. This will be deuterium, neutron plus gamma. So these are called photoneutrons, okay, and gamma reactions. So we will call it N gamma reaction. So in this case, you see this is the gamma radiation, and this gamma radiation is coming, and since this is loosely bound, we have seen this, and this will be hydrogen plus neutron. So these two reactions are neutron producing reactions. So this is important for the neutron producing reactions that we talked earlier. Okay. So as I said that for the reactor we need a neutron source, and this neutron source is usually we talked about it that it is radium beryllium. Okay, radium beryllium. You remember this radium beryllium source, or why we use this? Because we know this beryllium 9 reaction. This is beryllium 9, not 8, and 4 plus helium, this alpha particle 4 2. Okay, so this is alpha particle, that is helium, and this gives, you remember you wrote it already, this problem, and this will be carbon 12 plus neutron. Okay, neutron 1 0. So this is 9 2, then this is carbon 6 7 4 6 plus neutron 0. So this balances the conjugate. So this is the reaction that we started. You have written it though. Okay. So what you see that we need for this beryllium, we need a helium nucleus, that is the alpha particle. But where do you get the alpha particle, or where do you get this gamma radiation for the beryllium 8? Or for this reaction, beryllium, we need helium, and for this reaction, we need gamma particle. We need gamma particle. So we shall have to have a source of this helium nucleus, and for this the gamma source. And this gamma source is antimony. Antimony. What is antimony? Antimony is Sb, I think. Sb, I think it's around 124. Sb 124. Maybe Sb 124. Okay. I think it is 53 or something like this, around this number. Okay, you can check it. So this Sb it emits gamma radiation, and this gamma radiation, here we use this gamma radiation. So with this hydrogen, when we use antimony, we can get these neutrons. These neutrons we call photoneutrons because this gamma radiation is coming in. And for the radium beryllium source, for this reaction, we need what we need, as we say that we need radium. As I talked in the previous lecture, either it can be beryllium, it can be radium or plutonium, and radium, and usually radium is better because the number of neutrons is high in this case. So this radiative capture here, so here the neutron is captured by the nucleus and we get gamma radiation. This is radiative capture, and the charged particle is N alpha. We get charged particles or proton here. And then we talked about this neutron producing reaction. You see here in the book, the N2N reaction is especially important in reactors containing heavy water or beryllium. These are the equations that time runs so fast. So these are the reactions especially important for reactor containing heavy water and beryllium, since they have loosely bound neutrons. And we have seen, I have shown you this. This is the reaction, and this is the reaction. The other reaction with beryllium-8. What else? And we, as a source of the alpha particles, we use radium, beryllium, beryllium, and for gamma we use antimony, because these needs these other sources of the alpha particles or gamma radiations. And okay, so we have this charged particle reactor and neutron producing reactions. This is very important, and please, study. We shall have to study it more. We will do it. In fact, we will have lots of other stuff then. And there are other sources. Yesterday I told you about the californium source, and there is other source of. It's a spontaneous fission, and spontaneous fission sources like from the californium source, and from this californium, it reflects kind of the fission spectrum. That's why we used it in the laboratory, and the flux is very high. The interaction that this produces quite a good amount of a big amount of neutrons. Like say it is so another neutron source, neutron producing reaction for the neutron producing reactions, another is californium. I think it's 252 or something like this. Californium, and this californium undergoes spontaneously to fission, and it produces neutrons, and the neutrons are something like 2.34 into 10 to the power 12. 10 to the power 12 per second per gram. That's why californium source, when you buy californium source, you buy in grams. Okay. And then we have another important reaction, actually, for the reaction for which this subject is about all about this and fission. We write it, we just write and then F. A neutron comes and fission occurs. Well, this is our subject actually. This we shall have to treat. Actually, this is the reaction that for which this subject is all about. So what happens? This nucleus, you know it. The neutron comes, forms a compound nucleus, and the neutron split. We get a new, new materials and energy. Lots of energy, about 200 MeV per energy, and this is the principal source of energy, nuclear energy that we are harnessing today. And many of these reactions that I already mentioned that involving the formation of the compound nucleus, scattering reaction, both elastic and inelastic, neutron first obtained from a compound nucleus, atom are uncharged, mass number increased by 1. Of course, the mass number will increase by one number. The nucleus decays via neutron emission to produce the original nucleus plus a neutron. The product nucleus is left in the ground state and excited stable according to the scattering. But anyway, we will talk actually. This is about our subject, the emission of gamma rays and fission. To understand this, we need to understand some parameters. Okay, if I summarize this now, because we don't have much time. If I run out of time, we have left 5 minutes only. If I run out of time, I just want to finish today's lecture. Just I give you a summary. I give you a drawing so that you can easily summarize this. The neutron in the reactions between the neutrons and the nuclear, two main groups. One is scattering, another is absorption. We have seen all these reactions. There are 6 types of reactions. These are either scattering or absorption. Absorption is in where we N gamma. We see that this is an absorption reaction, and also N fission is an absorption reaction. We will talk a lot on this. In the scattering, we find the result is an energy exchange between the two particles involved, and consequently, the incident neutron remains free after the interaction. In contrast, the absorption of neutron, the scattering and absorption, we have two processes, absorption and scattering. By scattering of absorption, absorption of the neutron is captured by the nucleus, forming a new particles. So absorption, when it is absorbed, we get a new particle definitely. And for nuclear reactors, the most important absorption reactions are radiative capture and fission. So this radiative capture that we have talked about and fission. This radiative capture and fission are the most important reactions for us to study, as these two processes compete. While there is a fission, it can end up just by giving a gamma radiation. So these two processes compete, and that gives why we have U-238 and U-235 fission, fissile material, etc. So we'll talk on this N gamma reaction. Remember this N gamma reaction and N fission reactions. These are very important since these radiative capture. Okay, this is radiative capture. So we have radiative capture is that the neutron comes and gives out gamma radiation. The radiative capture and fission, the neutron comes and occurs fission occurs, and these two are these two compete. These two processes compete, and we will see. And the actually classification of the fissile material and the efficiency of reactor calculations. All this depends on this on these two processes. So finally, what we had elastic scattering. In elastic scattering, radiative capture 3. Number 4 is charged particle reactions. Number is neutron producing reactions and nuclear fission. So please remember how many. I think we have 6 reactions. elastic scattering, inelastic scattering, radiative capture, charged particle reactions, neutron producing reactions, and nuclear fissions. These are very, very simple stuff. I just, if I summarize this I give you a figure like this. This is our nucleus. We heat it with a neutron. This is 1 and 0. This is A and Z. So there can be in this elastic scattering directly and, okay, or there it can make a compound nucleus. This will be A plus 1, and this will be Z. And this is in excited state, and this compound nucleus, is about 10 to the minus 13 seconds or something like this. So this then decays, okay? This decays to it can be elastic scattering also, and okay, if I write in terms of this X, then it will be X A. This is X is the isotope, okay? We are the nucleus that we are thinking at the target, and this Z plus this will be inelastic scattering, and there can be radiative capture. Else we can have charged particle reaction. So just with the arrow I write here. So this will be added with this arrow, okay? I'll just take a few minutes. So this will be, it can be from this. It can be starting from this reaction, the same reaction you continue, okay? It can be X is our isotope. This will be Z minus 1. One proton is gone, and this will be A minus 1, A minus 1 plus proton 1. Okay, and this is what this is actually NP reaction. This will call the NP reaction. A neutron is coming and the proton is coming out. Or it can be X Z minus 1, Z minus 1, A minus 1 plus neutron. Okay, or this can be X Z minus 2, then here get A minus 3, A minus 3, A minus 3 plus alpha 4 and 2, and this is N alpha reaction, N alpha, we call it N alpha. So all these are charged particle reactions, okay? All these are charged particle reactions, and then what else we can have N fission, or we can have all N fission and fission. This is the reactions that we'll be talking a lot. So we can. So to understand all these mechanisms that we talked about, that is the interaction of the neutrons with matter. So we shall have to understand this, we shall have to have some parameters, with a number of parameters. We shall have to have number of parameters to understand all these reactions that we have written, and the number one parameter and the most important parameter is the cross section. So inshallah, in the next class, we'll be talking about the cross sections. Okay, thank you very much. And I hope that we will have our next lecture on Thursday. This